Okay, so we'll start with the design of circular water tank with flexible joint between floor and wall. Okay, we'll start with the design. Okay, so design problem or design statement is given like this: design a circular water tank. Design a circular water tank with flexible base for a capacity of 450 kiloliter. Okay, the depth of water is 4.5 meter and allow a suitable freeboard So this is the problem statement. So we'll start with the design directly. Okay, so given data, the problem statement is design a circular water tank. Design a circular water tank with flexible base for a capacity of 450 kiloliter. Okay, allow the depth of water is 4.5 meter. Allow suitable freeboard. So we have, let us consider, use M30 concrete and Fe415 steel. Okay, M30 concrete and Fe415 steel will be using. Okay, if no grade of concrete and steel are given in your problem, you can assume, but it shall be complying with the requirements of IS 456 and 3370 IS 3370 1967 2009. Okay, we have the capacity of water tank. Is equal to 450 kiloliter. Okay, just a minute. Okay, so we have capacity of water tank as 450 kiloliter. Okay, so in terms of liters, it will be 450 multiplied by 1000 liter. So this will be equal to 4,50,000 liters. Okay, we can convert it into cubic meter. Just divide this with 1000. So we'll get 450,000 divided by 1000 cubic meter. Okay, so this will be 450 cubic meter. Okay, if you directly know the conversion from kiloliter to cubic meter, you can write here 450 cubic meter like this. Okay, so this is the capacity. Now let us consider a freeboard of 200 mm is provided. Okay, a freeboard of 200 mm is provided, and we have been given the depth of water tank as 4.5 meter. We have been given the depth of water tank is 4.5 meter. Therefore, the effective depth of your water in the water tank, as freeboard is 200 mm or 0.2 meter, the effective depth of water in water tank, this will be equal to this 4.5 minus 0.2 meter, that is equal to 4.3 meters. Okay, so now we know that volume of water tank is equal to, we know this area, cross sectional area, pi by 4 into d square. This is your d multiplied by, okay, the height of your water tank. Okay, that is height of water. Oh, sorry, let us consider this as h. Okay, so this will be H, so this will be equal to pi by 4. We have volume of water tank is 450. We have this is equal to 450, okay, cubic meter. Pi by 4 divided by multiplied by d square, and we have H is equal to 4.3 meter. We can consider this d will be equal to square root of 450 multiplied by 4 divided by pi into 4.3. so we get this diameter is equal to 54 meter, 11.54 meter. Let us consider it is nearly equal to 11.6 meter. So take this value 11.6 meters. So diameter of our water tank is 11.6 meters now. Okay. Now some values we can get from the IS code. That is, first value we have to calculate get is sigma CBC. Then we have to find out the value of sigma BT. Okay. Then we have to find out the value of sigma CT and the value of sigma ST. Okay. All these values can be found out from either the tables I have shown you here in these tables. Okay. These three tables are there, or otherwise you can also refer this IS 3370 part 2 2009, where you can get all these values. So we have this value of sigma CBC as we'll get the value of sigma CBC here, that is 10. Okay, you can see here the value of sigma CBC is given. Value of sigma CBC for M30 grade is 10. Okay, so value of sigma CBC is equal to 10 Newton per mm square. Then we have to find out the value of sigma BT, that is tensile stresses in concrete. You can get the value of sigma BT here. Okay, in this table number 1 of IS 3370 2009 part 2. Okay, for M30 we have sigma BT as 2. here, so you can write 2. Then we have to find out the value of sigma CT. Which is given here, that is 1.5 for M30. It is 1.5, and we also have to find out the value of sigma ST. So sigma ST, we can get the value of sigma ST from this table number 4. We can get the value of sigma ST for tensile stresses in members under direct tension and bending and shear. The value of for high strength deformed bars is 130 Newton per mm square. So we get sigma ST as 130 Newton per mm square. So we have got all these values. Okay, these all values are obtained from IS 3370 part 2 2009. Okay. So we'll go to our problem. Okay, so we have got this sigma CBC. Okay, sorry. So we have got sigma CBC is equal to 10 Newton per mm square. Sigma BT, we have got it as 2 Newton per mm square. We have got this sigma CT as 1.5 Newton per mm square, and sigma ST as 130 Newton per mm square. Okay, so we have got all these values from IS. Okay, write down here IS 3370 2009 9 part 2. Okay, all these values are obtained from IS 3370 2009 part 2. Okay, from these values, okay, we can calculate the value of modular ratio. We know this modular ratio for this formula is 280 divided by 3 sigma CBC, 3 sigma CBC. So we can write down here 280 divided by 3. We have sigma CBC as 10 Newton per mm square, so this will be equal to 9.33. Okay, so we get the value of m, that is modular ratio. Now we'll start with the design for hoop tension. Okay, so write down either step number 2, we can consider the above portion as step number 1. Okay, design for hoop tension. Okay, so we know that if this is our water tank, if this is our water tank, okay, in plan, then it will be subjected to some forces from hydrostatic pressure from water in all the direction. Okay, due to which what will happen, some hoop tension will be developed and it will cause tensile stresses in the concrete or wall. Okay, so we have to design this wall for hoop tension. Okay, so the hoop tension T, the formula for calculating hoop tension T is given by gamma h into d by 2, where T is the hoop tension, gamma is the unit weight of water, h is the height of your water tank, and d is the diameter. So we can get this as, let us consider this gamma is 10 Newton per mm Newton per mm cube. Then we have h as 4.5 meter and diameter we have just calculated, that was 11.6 divided by 2. So we get this value of hoop tension T is equal to 261 kilonewton per meter height of wall. Per meter height of wall, we have got this hoop tension as 261 kilonewton per meter. Okay, now we have to calculate the steel required. Okay, so AST required, this will be equal to hoop tension T divided by sigma ST. Okay, because we know that sigma ST, this is equal to T divided by AST required. Okay, so just put the values. We have got this T is equal to 261 into 1000. Okay, because it is per meter height, therefore multiply it with 1000 divided by sigma ST. We have obtained this value from IS 3370, that was 130. So AST required is 2008 mm square. 2008 mm square. This is the AST required in the wall in terms of circular rings. Okay, in terms of circular rings throughout the wall, like this. If this is your wall, if this is your wall, what we'll be doing, we'll be providing these rings of cross sectional area 2008 mm square, like this. Okay, circular rings. Okay, so AST required is 2008 mm square. Okay, let us use 20 mm 5 bar, 20 mm 5 bars. Okay, so spacing required, we know the formula, that is area of 125 bar divided by AST required multiplied by 1000. Okay, so put the values here only. So spacing required, this will be equal to area of 125 bar is pi by 4 into 20 square multiplied by this 1000 divided by area of steel provided or required, that was 2008. So we get the spacing of 156 mm. We get a spacing of 156 mm here, and hence provide 20 mm 5 bars hoops, okay, hoops or rings, whatever you call, at 150 mm. Let us consider it is equal to 150 mm, nearly equal to, at 150 mm center to center at the bottom of center of wall. Okay, why we are providing up to the bottom? Because at the bottom we know that this value of, okay, the pressure will be more at the bottom and it will be reducing towards the top. Okay, therefore up to half depth we will be providing actual spacing obtained, and above this half depth we will be providing double the depth, because it will result in economy, okay. Therefore the spacing of hoops can be increased near top. Why? Because the bending the hoop stresses developed in at the top will be less, say from 2 meter above 20 mm 5 hoops are provided at 300 mm center to center, because this is the maximum limit up to which we can provide the spacing. Okay, so minimum spacing required is 300 mm. Okay, now for design of your, okay, so actual AST provided, okay, this will be equal to 2090 mm square. Okay, now we have to find out the okay, now we have to calculate the thickness of your wall. We have to calculate the thickness of your wall. So thickness of your wall, of water tank wall, okay, this is required to be calculated. Now we know this, we have seen this formula, sigma CT, it should be greater than the tensile stresses in concrete. This should be greater than this value, that is T divided by A equivalent. Okay, A equivalent. Okay, this T divided by A equivalent, it can be written as T divided by 1000 T plus m minus 1 into AST. We know most all the things except this T in this equation. So this sigma CT is greater than, T is 261 into 1000 divided by 1000 T plus, we know m already calculated 9.33 minus 1, area of steel we have already calculated 2090. Okay, sorry, this was 2093. Okay, this was 2093. Okay, so we get, okay, at the same time we know that this sigma CT, this value is equal to 1.5. we have already calculated that. Okay, or we have obtained this from IS 3370. So 1.5 is greater than 261 into 10 raised to power 3 or 1000 divided by 1000 T plus 9.33 minus 1 multiplied by 2093. So just solve this equation on the right hand side. So we get 1.5 is greater, sorry, T this T is greater than 157 mm. Okay, so thickness of your water tank wall, it should be more than 157 mm. Let us provide this thickness of water tank wall is equal to 200 mm, and effective cover is provided as 30 mm. Okay, this effective cover should be provided as per the provisions of exposure conditions as per IS 456 2000. Okay, now we have calculated the steel required for hoop stirrups or hoops, but we haven't yet calculated the distribution steel. So we'll calculate the distribution steel now. So distribution steel, okay, now this distribution steel, this will be vertical. Okay, the stirrups or hoops or rings are horizontal, whereas this distribution steel, this will be vertical steel. Okay, now we know that as per IS 3370 detailing provisions, this vertical steel or minimum steel or distribution steel, it should be provided at 0.35% of surface zone. Okay, 0.35% of surface zone. Now we know that this thickness is less than 300 mm. It is less than 300 mm. Therefore, AST provided this should be equal to this AST provided this should be equal to 0.35 divided by 100, that is 30.35% of cross sectional area of surface zone, that is 1000 multiplied by 200 divided by 2. Okay, so we get this AST is equal to 350 mm square. AST is equal to 350 mm square, and thus provide 10 mm 5 bars. Okay, if we calculate the spacing will be approximately around 200 mm center to center. You can calculate the spacing by spacing is equal to pi by 4 into 10 square divided by AST, that is 350 into 1000. Okay, into 1000. Okay, so this spacing comes out to be 224.39 mm. Let us consider we provide at 200 mm center to center. Okay, so this is how the vertical steel or distribution steel will be required to be provided. And now we have to design the base slab. Base slab of this particular water tank. Okay, so step 3, design of base slab. Okay, now as this particular water tank is resting on the ground, providing a thickness of 200 mm will be sufficient. So as water tank is resting on ground, a thickness of 200 mm for base slab is okay. Okay, and the AST provided, that should be again 0.35% AST to be provided. Okay, of cross sectional area. So AST will be, again we have already calculated, AST will be equal to 350 mm square. Okay, and half of this AST, that is 175 mm square, it will be provided on each face, that is 175 on top face and 175 on the bottom face. Okay, so 175 on the top face and 175 on the bottom face. Okay, if we provide let's provide 8 mm bars. Okay, if we calculate the spacing will be around 250 mm center to center, 250 mm center to center. And finally the last step is drawing or detailing of reinforcement. Finally we have to check the drawing or detailing of reinforcement. So steel provided here will be like this. Okay, so steel provided will be like this. We'll be having okay, this thickness of this particular water tank wall, this is your water tank wall, thickness is 200 mm, the thickness is 200 mm. Okay, which is provided here. Okay, we have got steel reinforcement, we have to provide like this. Okay, you can also provide on the one face, that is on the outer surface. Okay, this is the rubber pad, shown here. Okay, it will prevent it will allow the movement of your wall. This is the sealing material, the sealing material is provided here. Okay, joint sealing material. Okay, strip painting is provided here, the strip painting is again provided here. Okay, here we can see strip painting is here. Okay, and the steel reinforcement, a mesh is provided at the top, and a mesh is provided at the bottom. The spacing of all the bars is 250 mm for the base slab. Okay, thickness of this particular base slab is 200 mm, the thickness is 200 mm. So again we have to provide some lean concrete or PCC layer below this particular water tank and a bitumen layer. Okay, you can see here a bitumen layer is provided below this water tank. It will again prevent the leakage of water. Okay, so this is how we will be designing the water tank. Again a freeboard of 2.2 meter is provided here, 0.2 meter is provided here. Okay, so these are the drawings for your water tank design. Okay, with this particular design is completed. Okay, thank you.